All right. So let's talk about 6.7. 6.7 is about moments, centers of gravity, and centroids. Um, so we're going to be talking about homogeneous laminas in this section. This is a topic that you'll come back to in third semester calculus towards the end of the course, and you'll talk about non-homogeneous laminas at that point. But in this section, we're going to talk about homogeneous laminas. And so what are those, right? So a lamina is an idealized flat object that is thin enough to be viewed as two-dimensional. Okay. The density of a lamina is its mass per unit area, and a lamina with uniform density is called homogeneous. So those are the ones that we're going to be looking at. Okay, so a homogeneous lamina with mass M and area A has density. So maybe I'll say, so it has density. Delta equals M over A. And so that's a pretty simple concept, but just to give you a quick example of that, example 1, a triangular lamina with vertices 0, 0, 0, 1, and 1, 0 has density delta equals 3. Find its total mass. Well, if its density is mass over area, then its mass is density times area, right? So first of all, we're going to say its total mass is its density times its area, right? We already know its density is 3, right? It's a uniform density throughout, so this must be a homogeneous lamina, okay? So its density is 3, so all we have to do is find its area. Now this triangle has vertices 0, 0, 0, 1, and 1, 0. So it's this triangle right here. So its height is 1, its base is 1. So the area of that triangle, 1/2 base times height, would just be 1/2. So we know that the density is 3, and we know that the area is 1/2. So that means the total mass of that triangle is 3/2. Of course, we weren't given units of measurement here. So we weren't told like the units of measurement for the density. Maybe this is like pounds per square inch or something, in which case its mass would be 3/2 pounds, right? But anyway, but that's the idea there. So that's density. Now, a lamina's center of gravity is the balancing point of the lamina and is denoted by x bar, y bar. And if you know anything about like means, this is x bar is the symbol that we use for the mean of a set of data. And so it makes some sense that like we would denote the center of gravity by x bar, y bar. I will say that when I say it's the balancing point, what I mean is that if you could imagine like trying to balance the lamina on your finger, right? The place where it balances, you know, without tipping, that's the center of gravity. And this definition is not quite a rigorous definition because it's possible that the balancing point could be a point that's not even on the lamina at all. So it's not quite accurate to say that it's the balancing point of the lamina, but you get the idea. I think it's the point that if it were on the lamina, you know, you could kind of hold it up and balance it on your finger. Okay. Now, in order to give a formula for the center of gravity, we need to know what moments are, right? And that's why we're talking about moments. So this is kind of a complicated concept to wrap your brain around conceptually. Moments are basically like the vertical and horizontal lines where it's the propensity of the lamina to sort of spin around an axis, I guess. So, but you know, for the purposes of this class, it's not totally necessary to get a good, solid, like physical understanding of it. I'm just going to give you the formula for how it's calculated. And you'll see why we need these here in a second. But the first moment about the x-axis of a lamina on a region R, so in all cases when I give these formulas, I'm imagining that the region R is bounded between a function f of x and then the x-axis over the interval AB, right? So it's you know, this kind of scenario. You've got, you know, A, B, and you know, this is the region R that we're talking about. Okay, so anyway, so the first moment about the x-axis of this lamina, you know, where this is, you know, f of x, so of this lamina is denoted by m sub x, and it's the integral from a to b of 1/2 times the density times f of x squared. Now the density here, we're not assuming here that the lamina is homogeneous, so this will work even if you don't have a homogeneous lamina, right? And so the density in particular could change depending on where you are in the region. So that's why it's inside of the integral there and maybe not outside the integral. But in a second you'll see how we fix that up when we're allowed to, when we start assuming that the lamina is homogeneous. Then we can take the delta out and we can kind of cancel it and stuff. But anyway, so this is the moment about the x-axis. This is the moment about the y-axis, and be careful, they're not the same, right? They're not the same. So this one is the integral from a to b of not 1/2 delta, but just delta, and then not f of x squared, but x times f of x dx. Right, so you've got different formulas for m sub x and m sub y, right? The first moment about the x-axis, the first moment about the y-axis. And again, kind of loosely speaking, this is the propensity of the lamina to rotate around a horizontal line, and this is the propensity of the lamina to rotate around a vertical line. Okay, so finally, we can give a formula for the center of gravity, x bar, y bar. So the center of gravity, x bar, y bar, of a lamina occupying a region R, and again, I'm thinking of the region R this way, but the center of gravity of the lamina occupying a region R is, x bar is the first moment about the y-axis divided by the mass. Okay. Now, we didn't talk about, we talked about, we gave an example just a second ago about finding the mass if you have a uniform density. But if you don't have a uniform density, if the density changes depending on where you are in the region, then this is actually the formula that you would need to compute the mass. Okay? And I'm not giving a proof of that fact. You can find a proof of all of this stuff on pages 384 to 386. But this would be how you would calculate the mass. This we saw a second, or sorry, this, I guess they're both the mass, right? So this is the formula for the mass. This is the formula for the first moment about the y-axis. Okay, so in other words, you can think of this thing as 1 over the mass of R times m sub y, right? The moment about the y-axis. Y bar is the first moment about the x-axis divided by the mass, right? So you could think of it as 1 over the mass of R times m sub x. So it's kind of interesting. They swap places, right? So for y bar, it's 1 over the mass times m sub x. For x bar, it's 1 over the mass times m sub y. In our case, because we're working with homogeneous laminas, the mass is going to be much easier to calculate. We don't have to do the integral. We can just do what we did in exercise 1 and realize that the mass is just the uniform density times the area, right? So the mass is just density times area in our case, since we're working with homogeneous laminas. So again, if you want a proof of this fact, you can read these pages of the textbook. I'm not going to write out a three-page proof of this fact, but if you're welcome to, you're welcome to look at these pages if you want to know what the proof is. So let's just practice putting these things into practice. So example 2. Let's find the center of gravity of the triangular lamina with vertices 0, 0, 0, 1, and 1, 0, and density delta equals 3. Okay, so this is the example that we just did a second ago, right? And in fact, I'm just going to kind of continue it along on the same page because it's the same example, really. Okay, so the center of gravity is going to be x bar, y bar. So we need to calculate both x bar and y bar. X bar is 1 over the mass of r. Well, we saw that the mass of r was 3/2, right? So I'm going to say x bar is 1 over the mass of r, that's 1 over 3/2, we just calculated it, times the integral from a to b. Well, so here's the picture, right? A is 0, b is 1, and I guess we need to come up with a function here, right? So we need to figure out what function is this. Well, it's a straight line, right, with a y-intercept of 1 and a slope of down 1 over 1. So this must be the function f of x equals negative x plus 1, right? Must be. Okay, so then the integral would be integral from a to b of the density, which is 3. So density 3 times x times f of x dx. Okay, so there's the setup for x bar. So it's not terrible, right? You're just kind of plugging some stuff into a formula. So this would be, well, 1 over 3/2 is 2/3. And then this 3 I can take out and cancel with the 3 in the denominator. So I'm just going to get 2 when all is said and done. So it's going to be 2 times the integral from 0 to 1 of, and I'm going to go ahead and distribute that x. So it's going to be negative x squared plus x dx. Okay, so then that's going to be 2 times negative x cubed over 3 plus x squared over 2 from 0 to 1. So that's 2 times. When I plug in 1, I get negative 1/3 plus 1/2. And when I plug in 0, I get 0 plus 0. Nothing interesting, right? Okay, negative 1/3 plus 1/2. So this would be negative 3/6 plus, or sorry, negative 2/6 plus 3/6. So that would be 1/6. And then times 2 would be 2/6, or in other words, 1/3. Okay, so there's x bar. Y bar is 1 over the mass of r times the integral from a to b of 1/2 times the density delta, which we said was 3, times f of x squared. Okay, so let's finish up that calculation. Again, this will be 2/3, and the 3 will cancel the 3 in the denominator. The 1/2 will cancel the 2 in the numerator. So all of those constants just cancel out. Wow, it couldn't be nicer than that, right? As for the negative x plus 1 squared business, you could either solve this with like a u substitution, or you could go ahead and expand it, whichever way you prefer. A u sub might be nice. In fact, you could almost do it in your head without doing a u sub, right? Because if you let u be negative x plus 1, then du is just going to be negative dx. So I can put a little negative dx here as long as I offset it with a negative out there. And then this is just going to be negative x plus 1 cubed over 3. So I'm just going to, well, okay, so forget that. So this is going to be negative. negative x plus 1 cubed over 3, evaluated from 0 to 1. Okay? And just to be sure, you can kind of work backwards, right? If you take the derivative, it would be 3 times negative x plus 1 squared over 3. So 3's will cancel, you get negative x plus 1 squared. And then chain rule, right, times negative 1. And the times negative 1 will cancel that negative. Anyway, so there you go. All right. So this is going to be negative. So I'll kind of think of it like this. If I plug in 1, I'm going to get 0. 0 cubed is 0. 0 divided by 3 is 0. So I get 0. If I plug in 0, I'm going to get 1. 1 cubed is 1. 1 divided by 3 is 3. So I get a negative 1/3. Well, that's just 1/3. Okay. Oh, that's kind of interesting. Look, you end up with the same number. That's just a coincidence. That's not always going to happen. But the center of gravity then, so the center of gravity x bar, y bar is, in this case, 1/3, 1/3, right? And that would be your final answer for that problem. So okay. So that's that example. Moving on. Okay. In the case of a homogeneous lamina, the center of gravity x bar, y bar of a lamina occupying the region R, again bounded by f of x and ab, is called the centroid of the region R. So if the lamina is homogeneous, then it gets a special name. Instead of calling it the center of gravity, we just call it the centroid. Okay. Now note that since the lamina is homogeneous now, the density delta is going to be constant throughout. Okay, it's going to be uniform throughout the region, so it's going to be a constant. And so we can move it out of the integral and then cancel it off. Okay, and so that yields the following fact. So the centroid, x bar, y bar. Okay, so in general, right, the center of gravity is given by these functions. But the centroid, if you know that the lamina is homogeneous, then instead of calling it the center of gravity, we just call it the centroid. And the centroid, you can cancel off that delta so that you just get these formulas, right? So you get, instead of 1 over the density, or sorry, 1 over the mass of R, you just get 1 over the area of R. And then you also don't have a delta in here. It's just integral from a to b of x times f of x dx. So that's for x bar. And y bar is going to be 1 over the area times the integral of 1/2 f of x squared dx, right? So it simplifies things a bit. And in fact, we saw that in the previous example, right? We saw so much cancellation going on, and it's because we had a uniform density, right? We had a uniform density, and that's why we got so much cancellation. So again, if you don't have uniform density, then you'll learn about how to deal with that in third semester calculus, right? Calc 3. Okay, so let's look at the next example. It says find the centroid. That's the center of gravity, right, for a homogeneous lamina. But let's find the centroid of the semicircular region below. And we're given this, well, it's supposed to be a semicircle, but it's a semicircular region. And it looks like the radius of the semicircle is just the generic number a. Okay, so let's see if we can do this one. See if I can still fit the formulas on the page. Okay, well, so first of all, we need to find the area of the region. And that shouldn't be too difficult because we know that this is just a semicircle, and we know the area of a circle is pi r squared. So the area of the semicircle would be 1/2 pi r squared, right? So the area And in this case, r is just a. Right? The radius is just the number a. So it's 1/2 pi times a squared. I suppose we could kind of clean that up, so we could call it pi a squared over 2. Okay? So that takes care of that first part. For the rest of it, we need to figure out what f of x is, right? We need to figure out what this function is. So for a semicircle, well, okay, so this is a circle centered at 0, 0 with radius a. So the equation for the circle would be x squared plus y squared equals a squared. But of course, we don't want the whole circle, we just want the top half of it. So we'll solve for y and take the positive square root. So y squared is a squared minus x squared, and y equals plus or minus square root of a squared minus x squared. But the negative is going to give us the bottom half of the circle, and that's not what we want. We want the top half of the circle. So we'll take y equals square root a squared minus x squared. Okay. So that's our function. And so I think we're ready to calculate now x bar and y bar. So x bar is 1 over area of r. So that's 1 over pi a squared over 2 would just be 2 over pi a squared times the integral from, oh, this is going to be kind of confusing now because a, b, and a, but here I meant just the limits of integration. So this is the left limit of integration, which in this case would be negative a, and this is the right limit of integration, which in this case would be positive a. So it's going to be the integral from negative a to positive a of x times f of x, which we just solved for. Dx. And that's not a terrible integral to have to compute, because look, you can do a u substitution and there's the derivative sitting out right there. Remember that a is just a constant. It's an unknown, but it's constant. So anyway, so here's how I'm going to do it. I'm going to say let u equal a squared minus x squared. Then du would be negative 2x dx. Also, we can fix up the limits of integration, I suppose. Although I may not want to do that because I've got an a out here, which I figure probably would cancel somehow. So I'm not going to change the limits of integration. I'm just going to calculate the indefinite integral and then go back and substitute back in later. But anyway, so in order to have the du, I need to have a negative 2 here, which is fine as long as I offset it with a negative and a 2 in the denominator, which will just cancel that one, right? So now I can replace negative 2x dx with du, and I can replace all this stuff with just a u. So I'm going to get square root of, well, actually, I guess I'll have the negative 1 over pi a squared times the integral of square root of u, du. So that's going to be u to the 3/2 divided by 3/2. So I guess I should have just said 2/3 u to the 3/2. Okay. Now I can back substitute and say, well, u was really a squared minus x squared. So this is 2 times a squared minus x squared to the 3/2 divided by 3. Oh, shoot, and I'm missing the negative 1 over pi a squared, right? So, and here I need it as well. So maybe I'll just do this. Pi a squared negative. Okay. But this I need to evaluate between negative a and positive a. Goodness gracious. Well, let's see. So I'm going to have negative 2. If I plug in a for x, remember I'm plugging in a to x. So So if I plug in a to x, I get a squared minus a squared to the 3/2 over 3 pi a squared. That's going to be 0, right? So I have that minus, if I plug in negative a, man, I'm also going to get 0. That's interesting. Okay, so all of that work to get 0, really. So I'm going to get minus a negative 2 times a squared minus negative a squared, which, by the way, is just negative a squared is just the same thing as positive a squared. So again, I'm going to get 0. So I'm just going to get 0 here. Okay, well, so that's that. That's that for x bar. So x bar equals 0. What about y bar? Let's see. So y bar is 1 over area of r times the integral from a to b. So y bar is 1 over area of r. That's 1 over pi a squared over 2. So I'm going to call it 2 over pi a squared times the integral from left limit of integration to right limit of integration, right? So from negative a to positive a. 1/2 times f of x, which is square root a squared minus x squared. F of x squared dx. Oh, and once again, that's not a bad thing to have to compute. Okay, let's do it. Okay, so the 1/2 will cancel the 2. So I'm going to have integral from negative a to a. The square here will cancel the square root, so it's just going to be a squared minus x squared dx. Okay, and then remember, I'm integrating with respect to x, so this a is just a constant, right? So I'm just going to get a squared x minus x cubed over 3. And I need to evaluate that. Ah, shoot, I keep forgetting this constant, right? 2 over pi a squared. 2 over pi a squared. Or not 2, 1, because the 1/2 canceled. So this should be a 1. My goodness. How many mistakes can I make? All right. Anyway, this needs to be evaluated from negative a to positive a. So I'm going to have 1 over pi a squared times, if I plug in a, I'm going to get a cubed minus a cubed over 3. If I plug in negative a squared times negative a would be negative a cubed, right? Negative a cubed. And minus negative a cubed over 3. So that's really a cubed plus a cubed. And then negative a cubed minus a cubed. Okay, so many negatives, but these two will cancel. And then this negative makes it negative again. So it's a negative a cubed minus an a cubed. Negative a cubed over 3 minus a cubed over 3. Okay, so it looks like I'm going to have a cubed plus a cubed. That's 2a cubed. And then negative a cubed over 3 minus a cubed over 3. So minus 2a cubed over 3. Okay, this should clean up a little bit. This would be 6a cubed over 3. So 6a cubed over 3 minus 2a cubed over 3 would be 4a cubed over 3. Okay, and then finally, the a squareds will cancel 2 of those a's. We'll end up with 4a over 3 pi, I believe. Okay, so there's y bar. So putting it all together then, right, so we've got y bar, we've got x bar is 0, y bar is 4a over 3 pi. Okay, and that'll do it for that example. Hang on a sec. Okay, and I'm back. So we just finished example 3. Okay, so we found the centroid of that semicircular region there. Okay, so given any radius a, right, this is going to be the centroid of that upper half of a circle. So that's kind of cool. Anyway, so I just have a couple more examples that I want to show you because, as always, we can the regions that we've been looking at have been, bounded between some curve f of x and then some interval along the x-axis. But you could have a curve that's bounded or a region that's bounded between a curve and the y-axis, right? Or you could have a region that's bounded between two curves instead of being bounded between a curve and an axis, right? So let's look at an example of each of those, right? So if the region R is bounded between two curves, f of x and g of x, then we do a similar calculation, right? So you'll notice that x bar is just like x bar up here, only we have to do f of x minus g of x, okay, instead of just f of x. And this is assuming, of course, that f of x is the top function and g of x is the bottom function, okay? And similarly for y, we just do f squared minus g squared, right, times 1/2. And the region of R, of course, would be the region between the area of R would be the area between f of x and g of x, which we talked about at the beginning of this chapter quite a bit. So let's practice doing that. Okay, so number 4 says, find the centroid of the region enclosed between y equals x squared and y equals x plus 6. Okay, y equals x squared and y equals x plus 6. Where do those things even meet? I guess we could set them equal to each other and solve. What would that be? -3, +2, right? So that means they meet at x equals 3 and at x equals -2. Okay, so that's where I'm going to have to draw the graph. At 3, x squared is 9, and x plus 6 would also be 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So they both go there. 2, 4, 1, 1, 0, 0. This is x squared, of course. -1, 1, -2, 4. So there's the x squared portion. And then the x plus 6 portion, well, it obviously goes through those 2 points. I guess we can verify that, right? -2, 4, sure enough. And 3, 9, sure enough. Its x-intercept is 1, 2, 3, 4, 5, 6. So it's this straight line. Okay, so there's our region. Okay, there's our region. Always good to have a picture, right? So I guess the first thing we should do is find the area of the region, right? So area of R is going to be the integral from -2 to 3 of f of x minus g of x. So that would be the straight line, which was x plus 6. Minus the parabola, which is x squared. Okay, so that's integral from -2 to 3 of -x squared plus x plus 6. Okay. So that's negative x cubed over 3 plus x squared over 2 plus 6x. I'm just going to use my calculator. Oh, my brain is maybe faster. 27 divided by 3 is 9. So we've got negative 9. 3 squared is 9 divided by 2 is 9 halves. And then plus 18. And then minus. That would be negative 8, positive 8, so 8 thirds. 4 divided by 2 is 2. And then 12. Okay, now I'll use my calculator. Negative 9 plus 9 halves plus 18 minus 8 thirds plus 2 plus 12. Oh, goodness. 149 over 6? You've got to be kidding. Well, there you go. Because we're going to have to use this thing now, right? We're going to have to carry this along with us through all the remainder of the problems. That's not going to be very fun. Oh, well. Hold on, let me double check. Let me double check. So I'm gonna do negative 3 cubed over 3 plus 3 squared over 2 plus 6 times 3 minus negative 2 cubed over 3 plus negative 2 squared over 2 plus 6 times negative 2. That's what it was. This should be a negative 12. Okay, so you should actually get 125 over 6. Not that that's any better. It's still a nasty thing we're going to have to carry through our calculation, but okay, so 125 over 6. All right, that's the area. So now I'm ready to calculate x bar and y bar. So x bar is going to be 1 over area of r, so that would be 6 over 125, times the integral from a to b, that would be negative 2 to 3, of x times f of x, so top function minus bottom function. So again, x plus 6 minus bottom function x squared dx. Which is interesting. That's almost what we did already, but it's not quite the same, I suppose. So we'll continue with our calculation. 6 over 125 times the integral from negative 2 to 3 of negative x cubed. I'm rewriting in descending order as I go. So plus x squared plus 6x. That's going to be 6 over 125 times negative x to the 4th over 4 plus x cubed over 3 plus, this would be 6x squared over 2, so 3x squared. From negative 2 to 3. I better use my calculator. So if I plug in 3, now I'm going to get negative 3 to the 4th divided by 4 plus 3 cubed divided by 3 plus 3 times 3 squared. Oh, just 3 times 3 squared. So that's 63 fourths. And then if I plug in negative 2, I'm going to have minus negative 2 to the 4th divided by 4 plus negative 2 cubed over 3 plus 3 times negative 2 squared. That's 16 thirds. Okay, So 6 over 125 times 63 over 4 minus 16 over 3 is 1/2. Holy schmoly. All of that comes out to 1/2. That's incredible. Okay, cool. Right, so there's x bar. There's x bar. Now we need y bar. Y bar is going to be 1 over area of r times integral from, so it's going to be 1 over area of r times the integral from a to b of 1/2 times f of x squared minus g of x squared. So again, that's top minus bottom. So f of x squared minus g of x squared. All right, so there's y bar. So let's do this thing. First of all, the 1/2 will cancel, the 2 here will cancel 2 there and leave a 3. So this is going to be 3 over 125 times the integral from negative 2 to 3 of, I'm going to have a negative x to the 4th. Then here I'm going to have an x squared, 6x and a 6x will make a 12x, and then a 36. So that's 3 over 125 times negative x to the 5th over 5 plus x cubed over 3 plus 12x squared over 2 would be 6x squared plus 36x evaluated from negative 2 to 3. Holy schmoly. Why do they have to make it so long? Well, okay. There's nothing for it. I mean, we just have to plug away, right? So this is going to be 3 over 125 times 3 to the 5th. Whoop. Negative 3 to the 5th over 5 plus 3 cubed over 3 plus 6 times 3 squared plus 36 times 3. That's 612 over 5. Now if I plug in negative 2, I'm going to have negative 2 to the 5th divided by 5 plus negative 2 cubed divided by 3 plus 6 times negative 2 squared plus 36 times negative 2. And that comes out to negative 664 over 25. 612 over 5 plus 664 over 25 times 3 over 125. Hold on, something went wrong. Oh, I'm sorry. It's negative 664 over 15. Let me see if that makes it any better. So 612 over 5 plus 664 over 15. Yes. Times 3 over 125 is... You're kidding me. So this is 4. So there's y bar. So y bar equals 4. Goodness gracious. Well, there you go, right? So the centroid, x bar, y bar, would be the point 1/2, 4. That's the balancing point. So all that work for 1/2, 4, if you can believe it. Okay, so that's that. Finally, now how long have I been going? 44 minutes? Goodness. I mean, all right. Well, so if r, so r could be just under a function and an x, between a function and an x-axis, or it could be between two functions, in which case you just have to subtract the functions. Or it could be between a function and the y-axis, right? So if r is bounded between the y-axis and some function w of y, well then you've got to switch things up a little bit. So x bar is usually, x f of x dx. This time x bar is going to be 1/2 w of y squared, right? Which looks more like the y bar formula. You see what I'm saying? So you have to switch things up, right? So x bar, now it takes on the formula of y bar from before, and y bar takes on the formula of x bar from before. It's x f of x, but everything's in terms of y, and you're integrating with respect to y. Okay, so let me give you this last example. Goodness gracious, what a long lecture. I guess this makes up for the short lectures we had this week, right? For the 2 short ones. But number 5 says, find the centroid of the region R enclosed between y equals square root of x, y equals 1, y equals 2, and the y-axis. Okay, let's draw it. So y equals square root of x. Goes through 0, 0, 1, 1, 4, 2. But we're bounded between the y equals 1 and y equals 2. So that's this thing. And the y-axis. So that's our region. Okay. Now, could you find the centroid by integrating with respect to x? Yes, but you'd have to split the integral here, right? So that gets kind of complicated. If you go with respect to y, it's easier because this is just the area, if you kind of tip it over, right? It's just the area under that curve, right? So you just change your perspective a little bit, and we'll do this with respect to y. So that means if this curve was y equals square root of x, then that means x equals y squared, right? So that's our function, x equals y squared, and we're going to be integrating from 1 to 2. Okay, so the first thing we would need to do is find the area, because we need to find the area of R first, and this is our region. So the area of R is going to be the integral from 1 to 2 of y squared dy. So that's y cubed over 3. So that's 8/3 minus 1/3. So area of R is 7/3. Okay, next thing we need to do is calculate x bar and y bar. So x bar is going to be the integral, 1 over area of R, so that would be 3/7, times the integral from c to d of function y squared, or sorry, 1/2 times the function y squared squared. Okay, so that's going to be 3/14 times the integral from 1 to 2 of y to the 4th. So that's 3/14 times y to the 5th over 5 from 1 to 2. That's 3/14 times 2 to the 5th is 32, so that's 32/5 minus 1/5. So 31/5, so 3/14 times 31/5 is 93/70. So x bar is 93/70. Okay, so there's x bar. And then y bar is going to be similar. So y bar is going to be 1 over area of r, 3/7, times the integral from 1 to 2 of y times w of y. That's y squared. Okay, so 3/7 times the integral from 1 to 2 of y cubed dy. That's 3/7 times y to the 4th over 4, evaluated from 1 to 2. 2 to the 4th is 16. 16 divided by 4 is 4. So this is 3/7 times 4. Let me do that again. 16 divided by 4 is 4, yeah. And then we plug in 1, we get 1/4. And of course we get fractions. Well, 4 minus 1/4. 4 minus 1/4 is 15/4, and then that times 3/7 is 45/28. So our centroid is 93/70 and 45/28. All right, that's the balancing point. And that's it, right? That finally does it for this section. So hopefully that's helpful to you.